Okay, thank you for coming. I'll be talking about possibilities of high angular resolution imaging with future amplitude and intensity interferometers. I'll start with some motivations, saying why we're interested in high angular resolution images. Then I'll discuss some of the capabilities of direct imaging with future amplitude interferometers. I'll talk about the limitations introduced by the atmosphere, wavefront distortion. Then I'll talk about a proposed solution to overcome this challenge of wavefront distortion with a modified laser guide star technique. And then I'll switch to another type of interferometry called intensity interferometry. And I'll show you some simulations of the capabilities of future intensity interferometers. Now, most stars start to appear as extended objects when our instruments reach resolutions of the order of 0.1 milliarc seconds. Now, this is equivalent to looking at an object of a few centimeters on the surface of the moon. If we would like to actually image objects that are this small, or if we would like to image structures that are this small, we need instruments that are effectively 1 kilometer in size if we want to image them at optical wavelengths. This is a simulation performed by Andrea Chiavasa of what the giant star Betelgeuse would look like if we would be able to observe it at visible wavelengths. So you can see the complex convection zones in the surface. These here are actual images obtained by current instruments, namely the Chaire interferometer and the VLTI. This image here is an image of the star Altair. Altair is a fast rotating star. As a star rotates very quickly, very fast, it becomes oblate. So you can see that the star flattens. And the poles of the star become closer to the center of the star, so they become hot. And the radiation increases. And you can see that the poles become brighter. So you can see that here the pole of this star is actually brighter. This was a very exciting image. It's one of the first images of the surface of a star. Now, sometimes these fast rotating stars, they rotate so fast and their poles become so bright that the radiation pressure becomes huge. And they can start to eject matter from the poles, such as the case of Alpha Arae. You can see that it's an oblate rotating star. It's very hot. And matter is expelled from the poles. So the list of possible science topics that you can explore is endless. Here I just mentioned a few. Now I'm going to present an example. I'm going to work a little bit with this simulated image of Betelgeuse. And I'd like to show you what it would look like if we had a gigantic telescope of, say, 60 meters. So the image that you would obtain is for those of you who like mathematics, it's a convolution of the pristine image and this gigantic pupil. And you can see that you already see many of the complex features in the stellar atmosphere. Namely, the smallest pixel that you can resolve is of the order of lambda, which is the wavelength, over the aperture. Now, technically, it's very difficult to construct a telescope that is 60 meters in size. So you can think of interferometry as masking a telescope. You can think that you put a mask and you use just small parts of a telescope. Or equivalently, you can think of putting two telescopes you can think of putting two telescopes on the ground, two small telescopes, if they're on the ground, you will have to compensate the fact that the light here is reached before than the light here, so you put a small, a delay line. Now, the image that you would obtain from just using two apertures is a set of fringes. And what's interesting is that as you increase the number of subapertures, here we have two, as you increase the number of subapertures, the image that you obtain starts to approach more and more what you would get with the full aperture. Now, this is, as I said, this is a convolution of the pristine image and this pupil, so you obtain replicas in the edges. Now, well, these results can be extremely improved if you use other techniques such as deconvolution techniques, but unfortunately I don't have time to talk about that. Well, this is a zoom of the central replica, and you can see that you essentially reach the capability of using a whole aperture with a diluted aperture. Now, this is all very nice, but in these simulations I did not include wavefront distortion due to turbulence. So here, what I assumed to obtain this image is that the wavefronts are nice and smooth, but what in fact happens is the wavefront is distorted at timescales of a few milliseconds and at spatial scales of a few centimeters. So let me show you what the image will look like once you start introducing distortions in the wavefront. As the wavefront becomes more and more distorted, you can see how the image starts to degrade until you essentially obtain a speckle pattern. So the conclusion of this slide is that you need to actively correct for these distortions introduced by the turbulence in the atmosphere. Now, because these distortions occur at timescales of the order of a few milliseconds, exposures in interferometry are limited to just a few milliseconds, and this limits the magnitude of the object that we can observe. So current instruments cannot go beyond magnitude 10. Another important challenge that I should mention is that current amplitude interferometers require delay lines. Now, this is a picture of the VLTI in Chile. And these rails, these rail-looking structures here are actually tunnels that contain the long delay lines, which are essentially like optical trombones. These are very, very difficult pieces of equipment to construct, and they must be made at with optical precision. And plus, they're quite expensive. There are some proposed solutions to avoid optical delay lines, such as the Carlina or spherical architecture by Professor Labeyrie. Now, this type of architecture avoids the delay lines, but the atmospheric turbulence remains a challenge. Intensity interferometrists have devised several techniques to deal with atmospheric turbulence. One of them, which I don't have time to talk about, but I'll just mention, is the phase closure technique for aperture synthesis. And this consists of combining light from 3 apertures. And you can show that the atmospheric phase shifts cancel out. What I'll talk about a little bit is the modified laser guide star for diluted apertures. Diluted meaning you don't have a continuous monolithic aperture, but several small sub-apertures. Now in conventional monolithic apertures, what is done is a powerful laser is pointed at this guy, and at 92 kilometers of altitude, you have the sodium layer, which is excited, and light is re-emitted incoherently. That is, you have a point source in the sky. And you can use, if you point the laser close to your science target, you can use the returning light as a reference for correcting the wavefront so that you can better observe your science target. Now, this conventional method for laser guide stars is not usable for hypertelescopes, mainly because hypertelescopes will be much larger than current monolithic apertures. So, in other words, the light from the laser guide star should sample the same atmosphere as light from the target. Now, I'll explain this a little bit better with a small diagram. If you have your star located essentially at infinity, and you have your sodium layer at 92 kilometers, if you use the atmosphere that is that the light from the laser guide star traverses is not the same as that from the star. So any correction that you apply coming from the sodium layer will not work. So a solution to avoid this cone effect is to have several laser guide stars coming from adjacent sets of subapertures. And here I show a diagram. So you have your many mirrors in the ground that emit light, emit light from a sodium laser. And at 92 kilometers of altitude, each quadruplet of subapertures that looks like this will form a small diffraction pattern in the sky that essentially, well, it looks like that. And well, two things are important to note here. One is that since you are using, since each of the quadruplets of subapertures creates its own laser guide star, the cone effect is avoided because the light from each laser guide star traverses the same atmosphere as the light from the actual science target. Another thing important to note is that this diffraction pattern here is sensitive. The shape of this diffraction pattern here is sensitive to relative path delays between adjacent subapertures. Let me show you an example. If you image those diffraction patterns in the sky with different delays between the subapertures, you will see that the shape of the diffraction pattern changes. So, for example, this corresponds to the atmosphere being in one under some conditions, and this is the atmosphere under another slightly different condition. I've started to make an initial laboratory setup to simulate this. These are actually computer simulations, and I would like to validate this in the laboratory. A way to simulate this is that you have a laser, and then this laser shines light through a mask that simulates your quadruplet of mirrors. That is, this is your pupil. And then you have a moving diffuser. You essentially have a motor with a reflective diffuser. The image that you obtain of the diffraction pattern here, you record it here in the camera. And in the camera, you record these images. And as I said, if you change the phase shift here, these diffraction patterns change. So I would like to quantify how accurately can we measure the phase with such a method. Okay? Now this is one way to deal with the atmosphere, but I would like to make a short pause and ask if there are maybe other methods to kind of avoid the sub-wavelength accuracy in the instrumentation. Now we can gain some insight if we understand interferometry in terms of correlations. Let me show you this example. I'm back to my two aperture interferometer, and I am in this example I'm observing a uniform disk-like star. Now what you will observe in the camera is a set of fringes, and this fringe pattern can be described as the squared sum of the complex amplitudes E1 and E2 received at each of the telescopes. Now this diffraction pattern, let me show you the profile. The sinusoidal part of the profile is coming from this interference term that some of you may be familiar with. Now what is nice is that interference term can be understood as a correlation between, as a time average correlation between the light received at one aperture and the other aperture. Now here on this right hand side plot, I'm showing the fringe contrast. That is to say, something proportional to the ratio of this maximum and this minimum. So you can see that the fringe contrast here is maximal, and that is shown here in this blue dot. And as I increase the separation of the apertures, well, you see less fringes. You see more fringes, but they are also less contrasted. So you see that the blue dot moved. And at some point, if I separate my telescopes enough, the fringes become less contrasted. Therefore, you can also say that the correlation between the light received between the two apertures has decreased. And at some point, the correlation will disappear. So the conclusion of this slide is that measuring correlations between the light received at two different apertures is equivalent to measuring fringe contrast. And you may have noticed that the fringe contrast follows precisely the Fourier transform of the irradiance distribution of the object in the sky. So I didn't prove this rigorously, but it has been done. I just didn't want to, I prefer to show a slide with an example than showing a slide full of mathematical demonstrations. Okay, now this leads me to define the complex degree of coherence, which is the time average correlation, the normalized time average correlation between complex amplitudes received at two different points in space-time. Amplitude interferometry has access to this complex quantity. That is, it has access to the Fourier transform of the object. But you can also correlate intensities. That is, you can record the electronic signals received at two detectors and correlate them. Now, it can be shown that when you correlate intensities, you have access to the squared modulus of the Fourier transform of the object in the sky. Now, this technique of finding the correlations between two subapertures was introduced by Hambury Brown and Twiss in the 1950s. So as I said, it consists of correlating intensities, and it can be understood classically. Imagine a star emitting light at two slightly different frequencies from two slightly different points. This detector A with its slow electronics, will be able to see the envelope or the beating effect between these two Fourier components. Telescope B, which would be close by, would detect a very similar signal, and therefore the correlation between A and B would be high. Telescope C will see a similar signal, but it will be shifted in time, so the correlation drops. And using this method, Hambury-Brown was able to measure the angular diameters of more than 30 stars in the 70s. Now, what is interesting about this is that this technique is insensitive. It is not sensitive to path delays that are shorter than those set by the electronic time resolution. That is, if you digitize the data at 1 gigahertz, your instruments can have optical imprecisions of the order of 10 centimeters. That is, you can have you don't need high optical quality in your instruments to do intensity interferometry. So the main advantage of this technique is that it is insensitive to turbulence, and there is no need for sub-wavelength precision, which is a huge advantage. Now, to be fair, you need very large light collectors. They don't have to be very sophisticated. They can be quite inexpensive, but you need large light collectors and long exposure times. These were the original telescopes used by Hambury-Brown and Twiss in the 60s and 70s to measure the angular diameters of more than 30 stars. What is nice is that these telescopes were actually later used for a gamma ray experiment, for gamma ray astronomy, and they look a lot like current gamma ray telescopes. Now, I don't have much time to talk about gamma ray astronomy. It's kind of outside the interest of this talk, but it's worth saying a few words. The idea of gamma ray astronomy, or ground-based gamma ray astronomy, is that you have a very high energy particle, a very high energy gamma ray, a photon, that interacts at the top of the atmosphere. It interacts with a nucleus, and it generates a particle shower. This particle shower travels faster than the speed of light in the medium, and it generates Cherenkov light. Now, what these telescopes here, these gigantic telescopes, these are 12-meter telescopes, what they see is the light emitted by all of this cascade of particles. And they can, in turn, deduce the position and energy spectrum at TeV energies, that is, energies that are 10 to the 12 times more energetic than the photons that we see with our eyes. Now, this field has been extremely successful, and therefore there are proposals to create a much larger Cherenkov telescope array. It's known as the Cherenkov telescope array. It will consist of nearly 100 telescopes separated by up to 1 kilometer. Now, with their large light collecting areas, they are ideal stellar intensity interferometry receivers, and they can be adapted for intensity interferometry at optical wavelengths. A common question is people sometimes think that we want to do intensity interferometry at gamma rays. That is not true. We would like to use gamma ray detectors to observe at optical wavelengths. These future arrays will provide thousands of simultaneous baselines. There's currently a stellar intensity interferometry working group within the CTA collaboration. Now, what I did was I took a preliminary design of the CTA array, and you can see the telescope location here. I looked at what it would be capable of doing. So the longest baselines of the CTA array can be seen here, 1.4 kilometers. Here I show it in my baseline plot. And 1.4 kilometers, that sets the maximal angular resolution of your instrument, which is of the order of 0.01 milliarc seconds at short wavelengths. Now that is almost unheard of with current instruments. The smallest baselines of 35 meters set your field of view of the order of 1 milliarc second. What I did was you can simulate data, and you can see that the Fourier transform of the star, in this case it's a uniform disk-like star of 0.1 milliarc seconds after 10 hours of exposure time. You can see that it maps the Fourier transform extremely well. And you can see this is a two-dimensional map where you can see the Airy function. This is a fit to the data, actually. Now, from these simulations, we would like to, this type of data was used to measure angular diameters in the past. But we would like to do a little bit more than that. We would like to see if it's possible to actually recover images of these objects. Now, some of you may have noticed already that we only have access to the modulus of the Fourier transform of the object. We don't have access to the phase. So this is a challenge if we want to recover images. So one alternative is to, you can live with the fact that you can't measure the phase. And you can do some model fitting. If you know, if you more or less know the physical behavior of your object, you can parameterize your object within some model and fit your model to the data. You can also take your make a guess of what the image would look like and start iteratively modifying the image until you maximize the agreement between the Fourier transform of your guess and the data. And this is a kind of a maximum likelihood approach. Alternatively, you can try to recover the phase. So there are several proposals to do this. You can go to even higher order correlations. That is, not just find correlations between two detectors, but between three, for instance. Now, this may be even more challenging because typically you need, of the order for bright objects, you typically need exposure times of the order of an hour to obtain a statistically significant signal. With higher order correlations, you may need more. However, the people that investigate this, they claim that, well, you have more triplets than pairs in an array. So if you have more triplets than pairs, that might, in the end, give you more sensitivity. So it's an open question. It's something that I did not go in detail. I chose to explore an analytic approach. The idea behind an analytic approach is that the Fourier transform of an object of finite size is an analytic function. Okay? If this function is analytic, this poses severe constraints between the magnitude and its corresponding phase. It cannot just be any phase. It belongs to a certain set. Okay? So there are algorithmic ways to retrieve or to estimate the phase, at least through the theory of analytic functions. And I guess the heart of this is based in the classical Cauchy-Riemann equations from complex analysis. I'm not going to go into the detailed math here, but I can show you a one-dimensional example where you have your Fourier magnitude. And in this example, you don't know the phase. You just say, okay, I have an object. I take its Fourier transform. I take its magnitude. I forget about the phase. And from the magnitude data, you can estimate what the phase would look like. So the solid line here represents my phase estimation, and the dotted line is the real phase. And you can see that, except for a few points, they match fairly well. And you can see the comparison between the reconstructed image, which is the solid line, and the real image, which is the dotted line. And you see that they match fairly well. Now, what I did was I extended this to 2 dimensions and tried to analyze simulated data from future intensity interferometers. And what you do is you work in slices in the UV plane. So starting from a pristine image, for example, this is a star with a hot spot, which is a few hundred degree Kelvin, hotter than the rest of the star. From here, I simulate data as would be obtained with the CTA array, and I run it through some analysis that I developed. So the data of this, it can be fitted to a certain basis. Since I take many derivatives and these things, it's convenient to fit it to an analytic function. And the algorithmic solution to the phase yields an image that already starts to look close to what you started with. Now, I must remind you that I don't use phase information here. I retrieve it algorithmically from the magnitude. Now, since these images are sometimes not fully satisfactory, you can improve them by using other existing techniques that have been developed previously. For example, one is the Gershberg-Saxton algorithm, also known as the FENUP algorithm, where you go between Fourier space and image space, and in each space you impose certain very general constraints. For example, here the constraint is that from the Fourier magnitude data, I already know the size of the star. So you can say that anything outside of a certain radius is 0, and therefore you already improve your image a bit. And you can use other available analysis techniques, such as the tools that are currently become standard in amplitude interferometry, such as MIRA, which stands for multi-aperture image reconstruction algorithm, which essentially it's an iterative algorithm that maximizes the agreement between the Fourier transform of your guess and the data. And so you see that in the end you obtain something that, well, it's not too bad. Now you can go to slightly more complicated objects, such as stars with 2 hot spots. And you can see that this is the pristine image from which I start from. So I start from here, I simulate the data, and I obtain this. So you can see that that the position of the position and approximate size of the hotspots matches fairly well. Here you can work with even more hotspots, and this is data that you can achieve with within a few hours of observation on bright stars. In addition to this, we did a little bit of lab work to kind of replicate some of the Hambury, Brown, and Twiss original experiments, but with more modern equipment. So you have your light source that shines light on a pinhole, and this is essentially your artificial star. You need an incoherent light source, like a thermal light source, for instance. And you have a beam splitter, and you have 2 very fast detectors. And these detectors are your miniature telescopes. Now the beam splitter is put there so that you can effectively place the two PMTs at the same, at zero baseline. So at maximal correlation. And then one of them can be moved to change the baseline. And the correlator can be, well, data can be correlated in an analog way, as Hanbury, Brown, and Twist did, or you can use digital correlators, such as this gigantic National Instruments box. The light source, we had difficulties proving this. I mean, doing some initial tests with a true thermal light source. So we created an incoherent source, which with a much a longer coherence time, which is essentially shining laser light through some rotating ground glass, and that goes through your pinhole, and so that creates your incoherent source. And you can see some results where for different sized pinholes, you can see the Fourier transform of the pinhole, and you can measure its size fairly accurately. The solid curves correspond to the expected theoretical curves, and the error bars, well, they correspond to the measurements. In addition to this, there are two Cherenkov telescopes, two 3-meter telescopes at is it 24 meter baseline, and these are the experiment is called Starbase. It's outside of Salt Lake City in Utah, and it's at an interesting place. It's very near an interesting place called Seabase, where you have there are these naturally warm pools of water with salinity content that is very similar to that of the ocean. So the owners of this place, they brought some tropical fish, and they have a diving facility. So if any of you are ever interested, you can go and go and dive with some nurse shark, and at the same time look at our 3-meter telescopes. Okay, so in conclusion, obtaining the phase is the main challenge in both amplitude and intensity interferometry. Multi-aperture phased images can be obtained with a laser guide star technique. As I show you, you can try and measure the distortions introduced by the atmosphere with the modified laser guide star setup that I showed you. Well, more insight can be gained when you understand interferometry in terms of correlations. So amplitude interferometry measures the complex degree of correlation, and intensity interferometry measures the squared modulus. Electronics, current fast electronics, as fast as a few hundred megahertz or even a gigahertz, will allow to measure the squared modulus of the complex degree of coherence. Intensity interferometry is insensitive to optical imperfections. This is key. But it is less sensitive, at least if you exploit only one spectral channel. Now, sensitivity can be increased if you simultaneously observe several of these. The sensitivity increases at the square root of the number of channels. There are several alternatives to recover the phase. I explored one, but it seems like every time I talk to a different physicist, he gives me a new proposition for trying to recover the phase. And finally, well, these images can be used to constrain models and to further our understanding of astrophysical objects. Thank you.